Hi guys, welcome back to Set Course with Tanya. Today we'll be discussing about the part 2 of mass and balance, that is payload. So let's get started. Basic empty mass or the tar weight. Now the minimum weight of an aircraft including standard items for operation. So as the name suggests, it is the basic mass of an aircraft that does not have any fuel, payload or crew. Rather, it comprises of lubricating oil, fire extinguisher, pyrotechnics, emergency oxygen equipment, supplementary electronic equipment, and most important, unusable fuel and unusable fluids. So the fuel that cannot be used for propulsion or the fluids that cannot be drained. Now, when is an aircraft actually weighed? It is weighed first on the initial entry to service, followed by if the all-up weight of the aircraft is more than 2000 kg, it is done at an interval of 5 years, or unless if there is a major repair or alteration, it is done after that. Now, on every weighing occasion, a weight schedule is created. The basic empty mass and the center of gravity position, it is determined by the manufacturer. And every aircraft is weighed before the issuance of certificate of airworthiness. Or if an aircraft has been imported from a foreign country, then the weighing schedule issued by the manufacturer, or for that matter, the previous operator, it is considered as valid. And after the aircraft has been weighed, a licensed AME or a person approved for the purpose, they can prepare the weighing schedule and it has to be submitted to the regional airworthiness office. So this is about the basic empty mass of the aircraft. Traffic load, also referred as payload. It is the total mass of passengers, baggage and freight including any non-revenue load. Now we have the aircraft and its weight as the basic empty weight. We have crew on board as the variable load. We also have the passengers and their baggage on board as traffic load. What we don't have is the fuel on aircraft. So everything inclusive but not fuel is referred as zero fuel weight. Now the zero fuel weight under the structural limitations set by the aircraft manufacturer is referred as the maximum zero fuel mass. Then the fuel on board, which is actually the total mass of the fuel on the aircraft. Now fuel on board is divided into certain categories, which is the first one being start and taxi fuel. So the amount of fuel required to start the aircraft and taxi it from apron to runway is referred as start and taxi fuel. It is additional to the takeoff mass, so that no fuel required after the takeoff is consumed before that. Now the next one being trip fuel. The fuel required for an aircraft to complete its flight from airfield say A to B is referred as trip fuel. The contingency fuel, say due to bad weather, an aircraft has to make a hold over a certain airfield, or the fuel that is required to circumnavigate that bad weather is referred as contingency fuel. It is usually 3 to 5% of the trip fuel. Now this is very important because this is asked as such in the DGCA exam, that contingency fuel is 3 to 5% of trip fuel. Alternate fuel. If an aircraft is going from, say, destination A to B, and due to any emergency, it has to now deviate to destination C. So the fuel required is referred as alternate fuel. Reserve fuel. To cater any unpredicted emergency, the amount of fuel that we should have on board is reserve fuel. Now, captain's discretion, the fuel that is taken for economic or operational reasons. Now, the sum of all the fuel is referred as ramp or block fuel. Useful load. It is the sum of traffic load and usable fuel. Takeoff mass. The mass of the aircraft including everything at the start of takeoff run. Now remember, this does not contain our taxi fuel. If this takeoff mass is under the structural limitations, the maximum permissible limit of this mass is called maximum structural takeoff mass. And if we are considering the performance factor, so as wet runway, high temperature, the takeoff mass is referred to as performance limited takeoff mass. And the lowest of the takeoff mass and the performance limited takeoff mass is referred as regulated takeoff mass. Now, maximum structural landing mass. The maximum permissible total aircraft mass upon landing under normal circumstances. It is again determined by structural strength of the aircraft. Maximum ramp mass, also called maximum structural taxi mass, is the maximum approved mass for commencement of ground maneuvers, so as taxiing. Now in DGCA exam, 2 to 3 numerical comes in every session regarding payload. So it is very important to understand how to solve numerical in exam. Now the step 1 is, if in question we are asked to calculate payload, we have to make a table like this and write certain values. The maximum takeoff weight, the maximum landing weight plus the trip fuel, and third, the maximum zero fuel weight plus fuel on board. We'll be given certain values and we'll be calculating these 3 figures. If in case the question is asking about the extra fuel, then we'll be taking about the lowest of this value and this value. But if it is a question that involves calculating the payload, we need to take the lowest of these 3 values and then substitute the lowest value in the equation, that is the maximum takeoff weight, which is the maximum weight at the commencement of takeoff roll, as the sum of dry operating mass, which was including the basic empty mass and the variable load, then the fuel on board and payload. Now let's take an example. The load sheet says aircraft weight with no fuel and no payload. That means this is the dry operating mass, which is actually the sum of basic empty mass and variable load. The M tau is being given. We have the route fuel, which is actually the trip fuel, and our reserve fuel as 3000 kg. So now our fuel on board would be the sum of trip fuel and reserve fuel, which is 18,200 plus 3000. That comes up 21,200 kgs. We are given with the landing weight and the zero fuel weight. Now let's make the table, which is M tau followed by maximum landing weight plus trip fuel, and then maximum zero fuel weight plus fuel on board. Now our M tau is 99,000, landing weight being 76500 plus our trip fuel which is 18200. This comes out around 94700. Our zero fuel weight as 74,000 plus fuel on board, which comes out around 95200. Now the lowest of this is this value. Substituting this value in our final equation, that says M tau, the lowest of the three values, is equal to dry operating mass plus payload plus fuel on board. Substituting the values we have, our payload as 10300 kgs. That is our final answer. Let's take another example. We have a structural takeoff mass, the landing mass, the zero fuel mass, dry operating mass, our fuel consumption, distance, reserve fuel, and true airspeed. And then we are given winds as headwind 20 knots till halfway, which then changes to 60 knots tailwind. We have to calculate the maximum payload in still air and then in winds. So let's take our first case, still air. Now we'll again make our table, which has maximum takeoff weight as 55,000. Then we have maximum landing weight plus trip fuel, followed by maximum zero fuel weight plus fuel on board. So let's calculate our trip fuel. How we will do that? We are given our distance and TAS. We know that speed is equals to distance by time. From here, time comes as distance 1500 nautical miles divided by our speed 260 knots, which is approximately 5.769 hour. Now we have our fuel consumption, which is 1600 multiplied by our time, as consumption is equals to fuel over time. From here we'll have our trip fuel as this, which comes out around 9320 kgs. Now we have our second case, that is the maximum landing weight plus our trip fuel, which comes out around 61230 kgs. Now our fuel on board, which is our trip fuel plus reserve fuel. Now zero fuel weight, which is 38000 plus fuel on board 9230, that is our trip fuel, plus 2750 our reserve fuel. This comes around 49980 kgs. So this is our lowest value. We'll substitute this value as the M tau in the equation. M tau is equals to dry operating mass plus fuel on board plus payload. Substituting the values, we get our payload as 9,000 kgs. This is the answer. Now moving ahead to our second case, that is calculation in winds. Now since we are given that the winds are varying midway, so we'll divide our distance of 1500 nautical miles into two parts. Point P being the midway. So now in first case we have a 20 knots headwind and our TAS was 260 knots. So our ground speed comes as 240 knots. Ahead of point P, we have a tailwind of 60 knots. TAS again being 260 knots. We have a ground speed of 320 knots. Now in the first case, our time would be 750 nautical mile divided by 240 knots, that is 3.125 hour. And in the second case, we have our time as 750 nautical miles divided by 320 knots, which is 2.343 hour. So our total time comes as 5.46 hours. Now we have got the time, we have the fuel consumption. Again, fuel consumption equals fuel divided by time. Hence we have our trip fuel as 1600 multiplied 5.46, which is 8749 kilograms. Now we'll again make our table. M tau as 55,000, maximum landing weight plus trip fuel, which is 52,000 plus 8749, which comes out around 60749, and maximum zero fuel mass plus fuel on board. Our maximum zero fuel mass being 38,000 plus our trip fuel 8749 plus our reserve fuel 2750. Now this comes around 49499 kgs. Now the lowest value being this one, we'll substitute in our final equation. That says m tau, the lowest of the three values, equal to dry operating mass, which as in this case is 29,000, plus fuel on board, our trip fuel plus reserve fuel, plus payload. And hence solving the equation, we get payload as 9,000 kgs. So this table is actually very important because at times in exam you are asked questions in where you have to convert mass to volume. And if you know the formula, it is very easy for you to calculate. And also at times in the payload question itself, there would be values given in different units. So you should always know how to calculate a certain figure from one unit to other. So if you can see, the boxes in our purple are of volume values, while that in green are mass values. So to convert liter to kilogram, we are multiplying it by specific gravity. And from kilogram to liter, we would then divide it by the specific gravity. From US gallon to liter, we have to multiply it by the value 3.7854. From liter to US gallon, we'll then divide it by the same value. In this way, conversions are made. Another important length related conversion is feet to meters, which is by multiplying it by 0.305. And distance, that is nautical mile to meter, is by multiplying it by 1852. So this was all for the part 2 of mass and balance, that is payload. Should you face any difficulty in understanding any concept regarding payload, just drop a comment in the comment section regarding your query and I'll be more than happy to help you. Or you can DM me on my Instagram channel, setcoursewithtaniya. Thanks for watching. Do subscribe for getting latest updates.